The point is that one of the central problems there's 2 or 3 central problems in solar physics, and one of them is to understand why the outer atmosphere of the sun is really hot. Because when you look at the temperature structure of the sun, you see that it's very hot in the center where the energy is constructed. Then it falls slowly, as we would expect, towards the surface. And at the surface, it's maybe 5,000–6,000 degrees. But then when you continue on into the solar atmosphere, it gets hotter and hotter. And that's very difficult to understand just from basic physical principles. And that's been clear since essentially the end of the Second World War or in the mid-40s, when people realized that the corona was hot. But what's also been realized, and essentially also that since that time, is that the magnetic field of the sun plays an important role in this. So my research has been trying to understand, along with everybody else who's doing this sort of thing in solar physics, how in the world does the magnetic field impart energy into the outer part of the atmosphere? And there's many ways of trying to figure that out. And one of the ways is to build so-called numerical models. And in numerical models, you put the physics that you know and you think are operating on the sun, and you put them into a computer, and then you turn on the computer and you let it run, and then you see what happens. And then the secret is, once you know what's happening, and when you think what's happening with the physical variables, the temperature is doing this, the magnetic field is doing this, the velocity is doing this, then you try to construct a set of observations that are synthetic, that would look like, what if your simulation was the sun? What does it look like? And then you take those simulations and you do them as well as you can. And that can also be very costly numerically. And then you compare them with the real observations. And in some ways, the best thing that can happen is that you're wrong, that they don't fit very well. Because then you can say, aha, something is wrong here. So let's change some of the physics, or let's add this effect that I didn't think was important, or whatever. You can do some changes. Okay, in the next 10 years, there's several things that are happening. One, which is maybe of interest to this talk, is that there are some very big solar telescopes coming that are being built on the ground. That's one thing. Another thing is that we have something called Moore's Law, which means that computers are getting better and better and better. So that means that we can be more and more ambitious when we build numerical models. And I think the combination of those two things, that I guess I should add a third thing, and that is that there will probably be some good satellite experiments also being launched. But I think it's the combination of these 2 or 3 things, depending on how you count, that will really be the exciting thing. I think if you want to talk more specifically, then one of the things theoretically that's happening now is that people are realizing that they can make models not only treating the solar atmosphere as a gas or a fluid, but can also concentrate on the particles that are being that are in the sun. I mean, instead of what you often do is you take all these particles, you put them in one box, and you say this is a fluid. It's like a cup of coffee or something. But you know in reality that the particles that make up that fluid are maybe not moving all in the same way. And looking into the details of how they're moving, that is something that could be interesting, and especially in this outer solar atmosphere, which is very thin. It's a very thin gas. Then perhaps those effects are really important. And I think that kind of effect is something that's going to be injected into the physics now in the next 10 years. The point here is that we want to understand how the magnetic field is moved by the atmosphere, and how energy transposes or goes along the field up into the upper atmosphere. So the new observatories will really help us with this, because what we want to look at is the small details of what is going on with the magnetic field. So we want to look at the magnetic field in high resolution and also in high time cadence. And measuring the field requires that we look at the polarization of light, because, well, the information about the magnetic field actually lies in how light is polarized by the magnetic field in the solar photosphere. And these new telescopes, I mean, 4 meters is a lot bigger than what we've had before. So the biggest telescopes that are around today are 1.5 meters. So that's almost a factor 3 in diameter, and it's a factor of 3 times 3 in area, right? So we're collecting a lot more photons. And the other thing that the big mirror will allow us to do is the bigger the mirror, the finer the details you can see on the surface of the sun. So what we would like to do is to see in detail how does a magnetic field come up to the photosphere, because it's generated deep in the solar atmosphere, and then it slowly bubbles up, and then it pops through the surface, and we know it gets stuck there for a little while. And then it gets moved around by the motions, and then some parts of it come into the outer atmosphere, and they're shaken, and maybe they meet each other and make so-called reconnection, little explosions. And all those details we want to capture. And I think the key to really understanding what's going on is to see those things in the highest amount of detail possible. So we want to measure how much field is coming up, how is it moved around, and at what time scales do things change. And we'd like to measure not only in the photosphere, but also in the part of the atmosphere in the sun that lies above that, that's called the chromosphere, the colored sphere, where things are a bit more difficult. And again, it will help to have a high resolution and a lot of photons that will come from the EST. Well, the EST can help get better data because the mirror is very big, and it can collect a lot of photons. In addition, a big mirror will let you see small details of the solar surface. And the good thing about the EST, or one good thing about the EST, is it's placed here on the Canary Islands, I mean probably on Tenerife or La Palma, where the conditions of the Earth's atmosphere are the best, or more or less the best on the planet. In addition, the EST will have multi-conjugate adaptive optics that will help remove even those small little errors that are going to come, because anywhere you have light coming through the atmosphere, then the light will be perturbed by that. But this adaptive optics will allow us to really sharpen our image in a pretty big field of view, and that will be a revolution for ground-based solar physics or solar observational astronomy. Ground-based telescopes, they are very good at concentrating on the so-called solar photosphere, where most of the light comes from, and also the chromosphere, which is some few thousand kilometers above in the solar atmosphere. Well, on the other hand, space-based telescopes, they don't have to look through the Earth's atmosphere, so they can see extreme ultraviolet and X-ray radiation, so they can see the upper parts of the solar atmosphere, which in some ways are very interesting to us on Earth, because a lot of the disturbances that come from the sun and disturb the Earth's magnetosphere and make space weather and other, destroy our satellites, or maybe even our electrical grids here on the ground, they come from that part of the atmosphere. But the point is that with space-based telescopes, you can see what's going on high in the atmosphere. With ground-based telescopes, you can see what's going on a little bit below. But what you really can learn from, because as I said, energy is going from the bottom of the solar atmosphere into the corona, and it's understanding how it moves from the ground, from the photosphere and into the corona, that is the key to understanding how the sun works. So you really need a set of observations from both, and you'd like to do them at the same time, so you can really see, if I shake here, it's going to say something over here. You can really follow that nicely. We all work together, and it's easy to move from Europe to the US, or maybe also to Japan, and work together with scientists there. But I think if you're going to have a good environment, just like the nighttime telescopes, it's good to have several telescopes, and it's good to have several groups that are competing, that are talking together, and that are doing this. And we know that right now the Americans are building a huge telescope on Hawaii, and I think that it would be very complementary that Europe does the same thing, and where we can actually come into some sort of competition, and a good-hearted competition that will help us build up a very good environment and keep the good environment we have here in Europe.